The atoms in your body were forged inside stars long before Earth existed. Imagine a cold, thin cloud in space slowly pulling itself together, like dust sticking into a snowball, until it gets so squished and hot it lights up and becomes a star. In this video you'll see that process in plain language, with everyday comparisons that actually make sense, and you'll discover why some stars die quietly and others go out in cosmic fireworks. We'll follow a star from birth to death using simple images, clouds turning into glowing balls, small stars fading like embers in a campfire, and giant stars ending in spectacular explosions that scatter the ingredients for planets and life. By the end you'll be able to explain to a friend, or impress at a party, how stars make the stuff we're made of. No PhD required, just a little curiosity and maybe a marshmallow-free campfire analogy. Cosmic nurseries, molecular clouds and the raw material. Most of the raw material for new stars lives in cold, dark clouds made mainly of hydrogen gas with a sprinkling of helium and tiny solid dust grains. These regions are much denser than the empty stretches between stars, but still extremely thin compared with air on Earth. They are also very cold, which helps molecules stick together instead of being torn apart by starlight. Molecular hydrogen, which is simply two hydrogen atoms bonded together, becomes common there because the dust grains act like tiny workbenches where atoms can meet and pair up. Dust also shields the interior from harsh radiation, like an umbrella that lets delicate chemistry happen inside. Inside these clouds the matter is not smooth, it is lumpy and full of motion. Turbulence, random, swirling motions of gas, creates dense pockets, while magnetic fields thread the gas and can slow down collapse. Some clumps, called cores, become dense enough that gravity wins and they begin to shrink, eventually forming protostars. External events can help too. A nearby explosion or a strong stellar wind can press on a cloud and trigger collapse, much like squeezing a sponge can force out a bubble of water. Not every clump makes a star, though. Only a modest fraction of the cloud's mass actually turns into stars, and much of the rest gets blown away. Tiny dust grains carry heavy elements such as carbon, oxygen, silicon and iron, the raw ingredients for rocky worlds and for the molecules of life. These grains stick together over time, growing from microscopic bits into pebbles and then into larger bodies inside the disks that form around young stars. Telescopes that see long wavelengths, like radio and infrared instruments, can peer into the dusty clouds and detect molecules such as carbon monoxide, which astronomers use as a signpost for where the gas is hiding. Observatories like ALMA reveal intricate filaments and rings, showing where material is gathering to build stars and planets. As stars begin to form they change their nursery. Radiation, winds and later explosive deaths shove gas around, carve cavities, and sometimes trigger new rounds of collapse in neighboring parts of the cloud. The process is messy and inefficient, lots of material is redistributed rather than used up. Think of it as a crowded garden bed where a few seeds sprout into strong plants while many others never make it, and the sprouting plants alter the soil around them. In the end, those dark, cold clouds supply the basic building blocks for stars, planets, and the chemistry that makes life possible, so every bright star in the sky started its life in one of these humble, dusty places. Gravity's slow persuasion, from turbulence to collapse. Cold, dark clouds of gas and tiny grains of dust float through space, and inside them random motions stir the material like wind in a storm. These clouds, often called molecular clouds, are the raw material for stars. They are cold and thin compared with the air we breathe, yet they can span vast regions and hold a lot of mass. Turbulence, chaotic, whipping motions of gas, keeps parts of the cloud from settling down, much like the way rough air keeps smoke from forming a straight plume. Picture a pot of soup being stirred, the spoon makes swirls and eddies, and until the soup calms the ingredients won't clump together. That simple kitchen scene is an everyday mirror of the tussle between motion and gravity out in space. Inside that chilly mess, gravity acts like a patient hand that never stops nudging. It works by pulling the slightly denser bits inward, bit by bit. Small specks of extra density are the places gravity first notices. They gather more gas, become denser still, and attract yet more material. This runaway process is called collapse, and it only starts where gravity finally overcomes the outward push of pressure and the stirring of turbulence. Think of a crowd gradually pressing toward a counter at a concert. One person moves forward, and the people behind close up the space. Slow, steady persuasion, no shove necessary. Resistance comes in several flavors. Heat inside the gas produces pressure that pushes outward and can halt collapse if strong enough. Magnetic fields threading the cloud act like invisible rubber bands, resisting squeeze. And rotation can sling material outward when a clump spins faster, like a spinning ice skater who extends an arm. All three can delay or reshape the collapse, so what might have been a single, neat fall inward instead breaks into parts. This breaking apart is called fragmentation. That's how one big cloud can yield many stars rather than a single behemoth. A good kitchen comparison is cookie dough that splits into many lumps, each lump bakes into its own cookie. As material falls inward, it heats up simply because squeezing something makes it warmer. A hot, dense center begins to form, surrounded by a flattened disk of leftover gas and dust. The disk comes from conserved spin. As the center contracts, the ambient rotation flattens the inflow, a bit like pizza dough spun in the air. Some of the gas in the disk spirals onto the central object, while some gets kicked out along the poles in narrow, fast streams called jets. Those jets can look dramatic when they interact with surrounding gas, like a garden hose spraying a muddy puddle and carving channels through it, and they are often a telltale sign that a young star is still feeding. The whole process is leisurely on everyday timescales and dramatic on cosmic ones. Turbulence can hold a cloud together for a long time, but once collapse begins it tends to accelerate, making denser and denser cores that will eventually light up from internal heat. In regions where many fragments form near one another, a cluster of stars is born. In quieter spots, an isolated star may emerge with a neat disk that could later form planets. Gravity is not a sudden bully. It's more like a slow, persuasive neighbor who keeps returning with increasingly convincing arguments until the porch is theirs. Protostars, the embers of future suns. Huge clouds of cold gas and fine dust slowly gather into denser knots, and where one of those knots becomes thick enough, the process of making a new star begins. Gravity, the invisible tug that pulls everything together, squeezes material inward. The raw ingredients are mostly hydrogen with a little helium and tiny grains of dust. Think of it as a cosmic flour and air mixture. As the gas falls inward, it heats up, and a glowing, swollen ball forms at the center. This early object is still feeding on its surroundings and is called a protostar. It doesn't shine like a mature star yet, but it does emit warmth and light, mainly at wavelengths our eyes cannot see. As the cloud collapses, it starts to spin faster because the same amount of spin gets squeezed into a smaller space, just like an ice skater pulling in their arms and twirling more rapidly. That spinning flattens material into a disk around the central object, a rotating pancake of gas and dust that keeps feeding the growing core. Material spirals down from the disk onto the protostar in fits and starts, and that steady infall makes the center hotter and brighter in infrared light. Telescopes that sense heat can peer through the dusty veil and reveal this hidden glow. The disk itself is also where bits of dust stick together and clump, and those clumps are the seeds of future planets, so a protostar is both a budding star and a nursery. Powerful narrow streams of gas often shoot away from the poles of the spinning system, cutting channels through the surrounding cloud. Magnetic fields thread through the disk and the young star and help launch these jets, which act like pressure relief valves that carry away extra spin and let more material fall inward. Those outflows can slam into surrounding gas and make bright knots and shocks that astronomers spot as moving features. It's a bit like a garden hose spraying into fog, creating streaks and puffs. The whole scene is messy and dynamic, with bursts of brightening when a clump of material suddenly plunges onto the protostar and dumps its heat, like a souffle puffing up and briefly collapsing, only much louder in the cosmos. If the central core gets hot and dense enough for hydrogen atoms to start fusing together, a stable, shining star is born and the protostellar feeding phase winds down. When the core never quite reaches fusion temperatures, the object remains a dim, failed star called a brown dwarf, more like a cosmic ember than a blazing sun. Protostars therefore set the stage for a wide range of outcomes: blazing stars that will light planets, faint brown dwarfs that smolder quietly, and disks that may become entire planetary systems. And for those who like a kitchen metaphor, the disk is the dough, the protostar is the oven, and sometimes you get a perfect loaf, and sometimes you get a slightly overcooked bun. Accretion disks and stellar babysitters. As a cloud of gas and dust collapses under its own gravity, it rarely falls straight in. The tiny bit of spin that the cloud had gets amplified and the material spreads out into a flat, spinning pancake around the forming star. This pancake is called an accretion disk, and the name just means a spinning ring of stuff that is slowly being swallowed by the central object. Think of it like water going down a bathtub drain. The swirl stays neat and flat because of the spin, and particles bump into each other as they move inward. A simpler everyday image is a pizza chef tossing dough. The rotation flattens and stretches the mass outward while the center stays denser. The disk acts like a cosmic babysitter, in the sense that it controls how quickly the infant star gets its meals. Friction and small collisions inside the disk let gas lose a little bit of its energy and fall inward, and that gradual feeding heats the inner parts of the disk and lights up the system. Picture a slow conveyor belt delivering food to a picky eater. The star gets fed, but not too fast. The same disk also traps dust grains and pebbles, letting them stick together and grow into planet seeds, which removes material that otherwise would have fallen straight into the star. In everyday terms, the disk is both the spoon and the babysitter who says, "Not all at once, please." Other kinds of babysitters show up too. A close companion star can act like a strict nanny. It tugs on the disk, pulls streams of material across space, or even steals some of it, and that can change the whole feeding pattern. This tug-of-war is similar to siblings fighting over the last cookie. One gets more and the other is left hungry, and sometimes the struggle makes sudden outbursts of light. Magnetic fields play a nanny role as well. They grab ionized gas and guide it onto the star along invisible tracks, producing bright hotspots where the material finally lands. At the same time, some of the inflowing matter is launched away along the star's poles in narrow jets, like a pressure relief valve or a garden hose squirting along a line. The way these disks and babysitters interact determines the star's final mass, how fast it spins, and whether a system ends up with planets. Some disks clear out quickly, leaving a lonely, fast-spinning star. Others hang around long enough for multiple planets to form, literally sweeping up the crumbs. Observations show rings and gaps in many disks, evidence that young planets can already be acting like little babysitters themselves by carving paths through the material. It's a tidy balance. Without the disk and its helpers, stars would gulp down all their gas and spin wildly. With them, the system evolves more gently, and sometimes the result is a whole family of worlds. Lighting the fuse, ignition of nuclear fusion. A star's core must be pushed and heated until hydrogen nuclei can get close enough to stick together, and that requires extreme squeezing and blazing heat. Protons, which are the heart of hydrogen atoms, carry positive charge and naturally push each other away. Think of trying to press two same-pole magnets together. Only when the crowding and temperature are intense enough can the short-range glue of the atomic nucleus take over and fuse those protons into helium, releasing energy in the bargain. Gravity does the heavy lifting by collapsing gas inward and turning that fall into heat, much like how a bicycle pump warms as you compress air. Pressure builds in the center and collisions become violent. In light stars like the Sun, most fusion happens through a step-by-step path called the proton chain, where two protons slowly combine and, through a couple of intermediate steps, end up as helium. Massive stars prefer a different route that uses carbon, nitrogen, and oxygen atoms to catalyze the process. This route is more efficient at higher temperatures. Either way, tiny bits of mass become energy. A little mass loss makes a lot of outgoing power, and that energy is what makes stars shine. Sometimes particles don't have quite enough punch to climb the repelling wall, yet they still get through by a quirk of quantum mechanics known as tunneling. Picture a ball that, against the odds, shows up on the other side of a hill without rolling over the top. Particles have a small chance to teleport through the barrier, and in the crowded, hot core those tiny chances add up. This is why fusion can begin at temperatures that, while extreme by human standards, are slightly lower than classical arguments would demand. It's a useful cosmic loophole, and slightly less polite than waiting in line. Not every clump of gas becomes a true star. Objects that don't gather enough mass get hot and squashed but never quite ignite sustainable hydrogen fusion. They glow faintly for a while and then cool, the astrophysical equivalent of a damp barbecue that never catches. Once real fusion starts, though, an equilibrium is established, the outward push from energy production balances the inward pull of gravity, and the star settles into a long, steady life. Tiny particles called neutrinos are produced in the fusion reactions and escape almost immediately. Detecting those ghost-like particles from the Sun provides direct proof that fusion is happening in stellar cores. This ignition process matters beyond astronomy. Understanding how stars light their internal furnaces informs efforts to harness fusion on Earth, where engineers try to replicate controlled versions of the same reactions. The cosmic recipe calls for enormous pressure, relentless heat, and a pinch of quantum trickery, and that combination is what lights the fuse in every true star. Main sequence life, the stable middle years. Stars spend most of their active lives steadily turning hydrogen into helium deep in their cores, and that steady fusion is what keeps them shining. At the center of a star, immense pressure squeezes particles together so that tiny bits of matter join up and release energy. This light and heat then push outward and hold the star up against gravity. The push from fusion balances the pull from gravity in a tidy, long-lasting tug-of-war, which keeps the star from collapsing or exploding while this fuel lasts. You can think of it as a perfectly timed stove burner, not too high, not too low, just right for cooking a very, very long cosmic meal. Energy produced at the core has to travel outward through different layers before escaping as starlight. In some stars, energy slips outward mainly as light, passing quietly through layers like a whisper. In others it rides on rising and falling currents of hot material, more like the bubbling of a pot of soup. The innermost zone where fusion happens is compact and fierce. Outside that, a region may let photons wander slowly for ages, being absorbed and re-emitted like a message passed hand to hand, and then an outer layer may churn and mix, bringing heat up to the surface. This internal structure explains why some stars have smooth, steady surfaces while others show more activity and flaring. A star's mass is the main thing that sets how it behaves during these middle years. Heavier stars burn hotter and brighter, living a more energetic but shorter steady life, while lighter stars burn more gently and can remain stable for a very long time. Color is tied to temperature too. Cooler, low-mass stars appear red, while the hottest, most massive ones glow blue-white. Our Sun sits in the middle of that range, a steady yellow star that gives Earth a reliable amount of light and warmth. Astronomers often plot stars by brightness and color to see this pattern. Most of the well-behaved stars line up along a band on such a chart, showing the clear relationship between mass, temperature, and brightness. The steady output of a main sequence star has practical effects for any planets nearby. Steady light supports climates, drives weather patterns, and powers photosynthesis on worlds like Earth, so a stable star is basically the universe's version of a dependable electric company. In everyday terms, a main sequence star is like a reliable friend who pays the utility bills on time. Boring, but absolutely essential. Astronomers use the light and color from these stars to figure out distances and to compare stellar families, because the physics behind their steady shine is predictable and well understood. So while the details involve pressures, particle collisions, and layers that behave differently, the overall story is pleasantly simple. As long as a star has hydrogen to burn and a mass that keeps things in balance, it will spend a long stretch of time as a dependable, glowing presence in the sky. Mass matters, how size rules destiny. A star's mass essentially sets its life timetable and the way it will end, because mass controls the pressure and heat in the core where fuel is burned. More mass means stronger gravity squeezing the center, which pushes temperatures high and speeds up the fusion reactions that make a star shine. Think of it like a camp stove. A tiny burner can simmer for ages, but crank up the size and heat and your pot boils over faster. Specific examples make this clearer. Red dwarf stars, which have far less mass than the Sun, burn their fuel very slowly and can last far longer than medium-weight stars, while the largest stars burn through their supply in just a few million years. Very low-mass objects sometimes fail to become full stars at all. If a newborn ball of gas can't reach the temperature needed to sustain steady fusion, it becomes a brown dwarf, a cosmic underachiever that glows dimly but never earns true star status. Red dwarfs, on the other hand, are small but stable, and because they mix their fuel efficiently they can keep shining for an extremely long time. The Sun falls into the middle class, big enough to finish its life in a dramatic way compared with red dwarfs, but not massive enough to explode like a heavyweight star. A practical life comparison: a red dwarf is like a slow-burning candle, the Sun like a kitchen oven set to bake, and a massive star like a barbecue left on high, short-lived and intense. When a star with roughly up to 8 times the Sun's mass runs out of the simple fuel in its core, it puffs up into a giant and sheds its outer layers, leaving behind a dense, slowly cooling core called a white dwarf. The shed material often forms a glowing shell that astronomers call a planetary nebula. In plain terms, medium-weight stars end by blowing off their clothes and revealing a hot core that fades over time, which is harmless compared to the explosions that follow in heavier systems. For stars much more massive than the Sun, fusion proceeds through heavier and heavier elements until iron builds up in the core, and iron is the troublemaker because fusing it doesn't release energy. Once the iron core becomes too heavy to support itself, gravity wins and the core collapses catastrophically. That collapse drives a supernova, an explosion so bright it can outshine an entire galaxy for a time, and the leftover compact object depends heavily on the original mass and how much mass was lost along the way. If enough mass remains, the squeezed core becomes a black hole. If a bit less remains, a neutron star results, an object so dense that a teaspoon would weigh billions of tons on Earth. Mass lost through strong stellar winds or stealing material from a companion in a binary system can change the expected outcome, which is why some stars surprise astronomers. And there's a cosmic payoff: those explosive deaths forge and scatter heavy elements, the iron and gold and other materials that eventually become planets, gadgets, and even us. So in the universe, size really does rule destiny, with consequences both dramatic and strangely useful. Binary romances and stellar drama. Many stars are born in pairs or small groups, so it is common for 2 suns to orbit each other rather than live alone. In these binary systems, the 2 stars pull on each other with gravity and trace out orbits around a shared center. Sometimes they are far apart and hardly interact, and sometimes they are so close that they profoundly change each other's lives. A companion star can steal gas from its partner when one expands, like a roommate raiding the fridge, and that stolen material can light up the system in spectacular ways. For Sun-like stars, roughly half are in binary or multiple systems, and for the more massive stars the fraction is even higher. Close binaries act like dramatic couples in which one partner ages faster because it lost weight. When a star runs out of the fuel that keeps its core puffed up, it swells into a bloated giant and can overflow the invisible boundary that keeps its gas bound. This overflowing gas flows onto the companion. Small transfers cause the companion to grow brighter and hotter, while violent transfers can form disks of swirling gas that glow in 10th rays. The process can be gentle or catastrophic. Think of it as slow flirting or full-on betrayal. A white dwarf is the dense husk left when a sun-like star finishes burning its fuel. It is about the size of Earth but contains a whole star's worth of matter, so it is extremely compact. If such a white dwarf sits next to a normal star and pulls gas onto itself, the accumulated hydrogen can suddenly ignite in a thermonuclear flash called a nova, a sudden brightening that fades over weeks or months. If the white dwarf keeps gaining mass and crosses a critical threshold, it can explode completely as a Type Ia supernova, leaving nothing behind and lighting up its galaxy like a dying flashlight. These explosions are used as cosmic mile markers because their brightness is remarkably consistent, which is handy for astronomers. When both members are massive, other outcomes appear. Massive stars can leave behind neutron stars or black holes, and binaries of these compact objects can spiral together as they lose energy. The final merging of two neutron stars or two black holes sends ripples through space, gravitational waves, that we can now detect, and such collisions can also seed the universe with heavy elements like gold and platinum. Sometimes the drama includes a gamma-ray flash, a brief and intense beam of radiation that would fry electronics across large distances if it pointed at us. Luckily, such bursts are very directional and rare from our vantage point. There are also slow-burning romances that produce odd results. In star clusters, a star that gains mass from a companion can appear younger and bluer than its neighbors, earning the nickname blue straggler. Contact binaries actually share outer layers, orbiting so close that they're practically fused at the edges, swapping heat and mass like an awkward couple sharing one blanket. And then there are runaway stars. A companion can be flung away at high speed when its partner explodes, like a dramatic exit from a soap opera. Observational tricks let astronomers track these relationships. When one star passes in front of the other, the total light dips in a pattern called an eclipse, a handy way to measure sizes and orbits. Spectra, the colored fingerprints of light, reveal shifts that tell us who is moving toward or away from us, allowing mass estimates without weighing anything. Even radio pulses from spinning neutron stars can mark timing changes that betray a hidden partner. These methods together let scientists untangle complicated romances written in light. Binary interactions shape not only individual stars but also the chemical makeup of galaxies and the kinds of explosions we see. Close companions can strip off outer layers so that a massive star explodes without its hydrogen coat, producing a different-looking supernova than a single star would. In short, stellar companionship leads to a wide menu of outcomes: peaceful coexistence, dramatic theft, sudden eruptions, and final mergers that echo across the cosmos. It is messy. It is cosmic soap opera. And it makes the sky far more interesting than lonely stars could on their own. Stellar spin, magnetic mayhem, and flares. Young stars often spin quickly, and that rotation sets the stage for a lot of the magnetic action we observe. As a cloud of gas collapses to form a star, the same amount of twist in the gas has to go somewhere, so the newborn object ends up turning faster, much like a figure skater who pulls in her arms and speeds up. That fast spin stretches and winds up the moving charged gas inside the star, which is what creates magnetic fields. Think of the star as a huge, boiling kettle of electrically charged soup whose motion makes invisible magnetic ropes. The Sun is a milder example of this. It spins and has a magnetic field that flips and wiggles, producing sunspots and occasional flares. The magnetic field acts in unpredictable ways when it gets tangled. Magnetic lines can twist and knot as different parts of the star rotate at different rates, and when those knotted lines suddenly snap and reconnect, they release a lot of energy in an instant. A good everyday comparison is snapping a stretched rubber band. You store tension and then get a sharp, sudden release. For stars, that release lights up the outer layers and hurls out particles in what we call a flare or a coronal mass ejection. The energetic burst can be bright across many kinds of light, from visible to tenth rays, and can blast nearby space with charged particles. Young, rapidly rotating stars are especially dramatic. Many of these young objects show huge starspots, darker, cooler patches on their surface, because strong magnetic fields suppress the normal hot bubbling there. Astronomers spot those dark patches as changes in the star's brightness, and from the pattern of those changes they can measure how fast the star is spinning. In the same way that Jupiter's fast rotation makes it bulge at the equator, a star's spin can subtly change its shape too, though you'd need precise instruments to notice it. Those magnetic wrecking balls also drive powerful winds that carry angular momentum away, which is why stars usually slow down as they age. Flares are not just light shows, they have practical consequences. When our sun flares, it can disrupt radio signals, knock out satellites, and paint the sky with auroras, little glowing curtains near the poles that are a direct result of charged particles slamming into the atmosphere. For planets around very active stars, repeated flares and particle storms can strip atmospheres or change their chemistry, so a habitable world needs some resilience or luck. Astronauts outside Earth's protective magnetic bubble face increased radiation risk during large flares, so mission planners watch solar activity carefully, and engineers design electronics to tolerate or shut down during big events. A pinch of humor helps. Stars are basically cosmic drama queens. They spin, get tangled up, and throw energetic tantrums. Yet the same processes that cause magnetic mayhem and flares also play a role in shaping planetary environments and in slowing a star's spin over time, so those outbursts are both destructive and part of a star's normal life story. Simple everyday analogies: a skater speeding up, a snapped rubber band, or a fridge magnet gathering iron filings, make the physics feel less alien, while the real consequences reach all the way to spacecraft, radio communications, and the auroral light shows we enjoy on Earth. Swelling up, red giants and supergiants. A star's outer layers balloon outward once the fuel at its center begins to run low. The core, where most of the burning happens, stops producing as much outward push. Gravity wins a little and squeezes the center tighter, which heats it up and changes where the burning happens. Instead of burning quietly all through the center, the star shifts to burning in a shell around the core, and that causes the outer skin to puff up like bread dough left too long near a warm oven. Think of the core as a campfire that has used up the best wood in the middle. Embers and flames keep flickering at the edges and the whole pile settles and spreads. The swollen envelope is much larger and cooler on the surface, and that change in temperature turns the star orange or red. Cooler surface means red color, but don't be fooled, because the surface area gets so huge, the star can still shine very brightly. In everyday terms, it's like a light bulb wrapped in a lamp shade. The bulb may get dimmer but the shade is so big that the room still lights up. The outer layers become very diffuse, more like cotton candy than a solid ball. If you could scoop a cupful of that gas it would be far less dense than air at sea level. Mass decides how extreme the swelling becomes. Stars about the size of the Sun generally become red giants, growing dozens of times larger and calmly shedding layers. Much heavier stars balloon up into supergiants, which can reach truly monstrous proportions and behave more wildly. Supergiants are unstable, they wobble, pulse, and blow off great gusts of gas in strong winds. A useful comparison is to think of a lightweight balloon versus a water balloon. One gives and settles, the other bulges and squirts unpredictably. Betelgeuse is a familiar example of a red supergiant. Aldebaran and Arcturus are examples of cooler, swollen stars closer to the red giant category. Pulsations and mass loss change how these stars look over time and can create spectacular surroundings. Some red giants brighten and fade like a slow, cosmic heartbeat. Other swollen stars shed enough material to form rings or dusty shells that catch starlight and glow. Observers with modest equipment can even spot the reddish tint of these stars, making them more than just faint points. And yes, a star in this phase could be jokingly called to be having a stellar midlife crisis, flaring up, losing weight in strange places, and changing its style, except instead of a new car it throws off layers of gas that might one day become new planets or dust in space. Planetary nebulae, beautiful farewells. A dying star similar to our Sun will gently shed its outer layers, creating a glowing shell of gas that astronomers call a planetary nebula. The process begins when the star runs out of fuel in its core and the outer layers are pushed away by a combination of pulsations and stellar winds. The leftover hot core shines fiercely in ultraviolet light, and that light makes the expelled gas glow like a lantern. In plain terms, the star lights up its own farewell confetti. This glowing shell is not the star itself, but rather the star's discarded clothing, illuminated by the small, hot ember left behind. Shapes of these objects can be delightfully strange and often beautiful. Some look almost perfectly round, forming rings like a cosmic donut, while others take on bipolar, hourglass, or butterfly shapes. A famous ring example is the Ring Nebula, M57, and the Helix Nebula looks uncannily like a giant cosmic eye. A close companion star can stir the gas into patterns, and magnetic fields or changing winds from the dying star can sculpt lobes and filaments. Think of it like blowing soap bubbles through a fork, the same soap and wind, but different tools and motions give wildly different results. Colors tell stories, too, because different gases emit different hues when energized. Hydrogen tends to glow red, and certain forms of oxygen often show up as green in photographs. That's similar to how adding metal salts to a flame in a chemistry set produces different colors. Astronomers read these colors to learn what elements are present. The glow fades over time because the gas expands and cools, so these nebulae are relatively short-lived on cosmic scales, lasting thousands to tens of thousands of years, brief fireworks in the life of a star. The end product is not extinction but recycling. The ejected gas returns carbon, nitrogen, and other elements to the surrounding space, enriching the material that will eventually form new stars, planets, and possibly the building blocks of life. The central remnant becomes a white dwarf, a very dense, hot object about the size of Earth but containing a large fraction of the original star's mass. Picture a peach pit squeezed down to pebble size but unbelievably heavy. For amateur stargazers, many planetary nebulae are rewarding targets through small telescopes, appearing as colorful, compact objects, like the universe's way of leaving a beautiful, useful mess behind. Core collapse and the spectacle of supernovae. Massive stars end their lives when their cores can no longer make outward pressure by fusing lighter elements into heavier ones. Fusion is the engine that fights gravity, and when that engine sputters, the center gives up. This is most obvious when fusion has built up an iron core, because iron cannot release energy by fusing into heavier elements. In simple terms, iron is the dead end at the bottom of the energy road. Picture a campfire that suddenly runs out of kindling. The flames shrink and the heat drops, except in a star gravity keeps piling on. The star's outer layers keep pressing inward, and the core begins a very fast collapse. As the core falls inward, atoms are crushed and electrons are forced into protons, producing neutrons and a flood of ghost-like particles called neutrinos that race outward. Neutrinos are almost invisible to matter. Trillions of them pass through a person every second without notice, so their role in the collapse is surprisingly dramatic despite their shyness. The collapse squeezes the core until it reaches the density of an atomic nucleus, a state so dense that quantum effects stop the neutrons from being pushed any closer together, a kind of hard floor to the squeeze. The result is a sudden halt and then a rebound, a violent cork returning after being pushed too deep into a bottle. That rebound launches a shock wave into the outer layers, but the story is not over. The shock can lose steam by breaking apart iron and by sending off neutrinos, and it can stall like a runner exhausted before the finish line. Fortunately, neutrinos coming from the newly formed neutron-rich center stream back into the stalled shock and deposit a fraction of their energy, helping to re-energize the blast. Think of it like a crowded elevator that stalls and then gets a shove from people outside. The shove is weirdly supplied by nearly invisible particles. When the shock finally pushes through the star's envelope, the outer layers are ripped off in a brilliant explosion. The explosion, known as a supernova, ejects vast amounts of material and creates heavy elements in the process. Elements heavier than iron are made in the extreme conditions of the blast and in the aftermath as neutrons are added to atomic nuclei. That means the calcium in your bones and the iron in your blood were forged in such stellar fireworks long before the sun was a thought, the universe recycling program at its finest. What remains at the center can be a neutron star, an incredibly dense object with a strong magnetic field and sometimes visible as a pulsar, sending beams of radiation like a cosmic lighthouse, or, if the core mass is high enough, the collapse continues into a black hole, a place where gravity wins so thoroughly that nothing, not even light, escapes. Some of the expelled gas forms colorful nebulae that astronomers can study, and a short-lived burst of neutrinos and a long-lived glow of light together tell observers that the spectacle has happened. Astronomers watch supernovae with many tools: optical telescopes to see the light, radio and 10th-ray observatories to study the expanding debris, and particle detectors to catch neutrinos that slipped through. Those neutrinos are a unique kind of witness, arriving before much of the light and carrying direct information about the core's collapse. The whole event is equal parts violent physics and natural artistry, a violent end that seeds the cosmos with the raw material for planets, chemistry, and life, which is one way the universe recycles its drama into dinner, house paint, and, yes, the occasional exoplanetary IKEA catalog. gamma rays, shock waves, and cosmic rays. Massive stellar deaths flood space with the most energetic light the universe makes, and that light is called gamma rays. They are just light, like the sunlight we know, but packed with far more energy, enough to knock electrons off atoms and change chemistry. Hospitals even use controlled gamma rays to zap tumors, which shows how powerful they are in small doses. When a star explodes or two compact stars collide, gamma rays pour out in a brief, brilliant flash or in a sustained glow, carrying information about the heart of the blast where temperatures and pressures go off the charts. Space telescopes catch these photons because Earth's air blocks them, and by reading the energies and timing of gamma rays scientists learn whether the collapse made a black hole, a neutron star, or a lot of new heavy elements, like reading a crime scene with light as the evidence. A moving front of pressure sweeps through gas and dust after a stellar explosion, and that moving front is a shock wave. Think of it like the ripples from a rock thrown into a pond, only these ripples are invisible pressure and they travel at thousands of kilometers per hour. They compress clouds, heat the gas, and sometimes push a quiet clump of material into collapse, sparking new stars. Supersonic jets on Earth make shockwaves too, which is the sonic boom you hear when a jet breaks the sound barrier. The idea is the same, just on a cosmic stage with much more mass. Shockwaves also heat and ionize atoms, strip electrons off, and leave behind glowing shells we can see in telescopes. Those shells are both funeral pyres and nurseries, depending on where you look. Particles called cosmic rays are born when shockwaves act like giant particle accelerators. Most cosmic rays are simple nuclei, mainly single protons, along with some helium nuclei and a sprinkle of heavier atoms. They are charged so magnetic fields tug and twist their paths across space. As a shockwave rams into interstellar gas, charged particles can bounce back and forth across the moving front, gaining a bit of energy each trip, like a ping-pong ball picked up more speed by two hands throwing it between them, until some escape as very fast cosmic rays. Those escaping particles travel far and wide and, when they hit Earth's atmosphere, they smash into air molecules and create showers of secondary particles that we can detect on the ground. All three, gamma rays, shock waves, and cosmic rays, are tied together in the life cycle of stars and in what astronomers actually observe. A supernova first sends out a shock that accelerates particles, and those particles can produce gamma rays by slamming into gas or by interacting with magnetic fields. Sometimes we see gamma ray light that maps where particle acceleration has been most efficient. Practical effects are nearby and surprising. Cosmic rays can flip bits in microelectronics on satellites, causing glitches, and airline crews get slightly more radiation on polar flights because some cosmic rays slip through Earth's magnetic shield there. It is poetic and a little cheeky that the death throes of faraway stars can nudge the formation of new ones and, at the same time, give our electronics a mild headache. Observing these phenomena requires different tools because each leaves a different signature. Gamma rays demand space observatories or high mountain instruments that catch the secondary flashes from the atmosphere. Shockwaves show up as expanding shells in visible or radio light. Cosmic rays are sampled by particle detectors on the ground and in space. Together they form a detective story. Gamma rays tell you about the most energetic processes, shockwaves reveal the mechanical push that rearranges gas, and cosmic rays carry away the particles accelerated by that push. The universe is messy, loud in its own way, and occasionally it sounds like popcorn, bursting, popping, and making new things from the leftovers. Birth of neutron stars and the pulsar lighthouse. A neutron star forms when a very large star uses up the nuclear fuel that kept its core pushing outward and suddenly cannot hold itself up against gravity anymore. The core collapses inward so tightly that protons and electrons are forced together into neutrons, leaving behind a tiny, incredibly dense object while the outer layers blow off in a giant explosion. Think of squeezing a soft pillow down until it becomes a tightly packed stone. The change in size and density is mind-bending, and the energy released is enormous. You can picture the outer shell of the old star flying away like confetti, while the new compact core sits at the center like a leftover marble made of pure neutrons. This compact core is roughly the size of a city but contains a mass comparable to a star, so its gravity is intense and its surface is exotic. Density is hard to imagine, so try a home example, packing the mass of a huge mountain into something the size of a small town, only then do you get close to the idea. The collapsing core conserves its spin, so if the parent star was rotating, the remnant spins much faster, like an ice skater pulling in their arms to twirl more quickly. That rapid spin, combined with a magnetic field that is millions to trillions of times stronger than Earth's, sets the stage for a cosmic light show. When the magnetic axis of this spinning neutron star is not lined up with its rotation axis, charged particles are whipped along magnetic field lines out near the poles and produce focused beams of radiation. Those beams shoot into space like the light from a lighthouse. As the star turns, the beam sweeps across the sky. If Earth happens to lie in the sweep, radio telescopes or 10th-ray detectors pick up regular pulses. A useful everyday comparison is a flashlight glued to a spinning toy top. You see a flash each time the beam points your way. These pulsing neutron stars are called pulsars, and some of them tick with startling regularity, stable enough that astronomers use them as precise timekeepers and as probes to study gravity and matter under conditions we cannot replicate on Earth. Not every newborn neutron star behaves the same. Some are energetic show-offs, flashing strongly at radio or 10th-ray wavelengths and slowing down only very gradually. Others are quiet, either because they spin slowly, their beams miss Earth, or they get shrouded by leftover debris. A few develop even stronger magnetic fields and become magnetars, which can release sudden bursts of energy in unpredictable ways. You can liken the population to babies in a nursery. Some cry loudly and get noticed, others sleep through the day, and a rare handful throw dramatic tantrums. Studying how pulsars are born and how they change teaches us about extreme physics, helps map the galaxy, and even aids in practical tasks like testing theories of gravity, all from objects that started life as ordinary stars but ended up as tiny, spinning beacons in space. When gravity wins, black holes form. A black hole comes into being when the core of a dying star becomes so compressed that gravity overpowers every outward push that had kept the star puffed up. Stars live by making a steady outflow of energy from nuclear reactions in their centers. That outward pressure fights gravity. When the fuel runs out, that pressure weakens and the core falls inward under its own weight. Picture a souffle collapsing when you open the oven. The structure that was holding everything up simply can't resist the squeeze anymore. When collapse begins, different outcomes are possible depending on how heavy the leftover core is. Smallish leftovers can settle into a dense, dim object held up by the pressure of tightly packed atoms. Bigger ones get squeezed until protons and electrons merge into neutrons, producing a neutron star, essentially a city's mass packed into something the size of a small island, where matter is crammed so tightly it behaves unlike anything in everyday life. If even that neutron-packed state can't support the weight, nothing left in normal physics can stop the implosion and a black hole is formed. Think of it like stacking too many books on a small stool. Beyond a point the stool collapses and the stack falls through. A defining feature of a black hole is the boundary around it from which nothing can return, not even light. That boundary is called the event horizon, and crossing it is like going past a waterfall's edge where the current is forever downstream. Getting back out is not possible. At the very center, classical theory predicts a point of extreme compression where our usual laws of physics break down, and scientists expect quantum effects to matter there but do not yet have a complete description. Although that sounds scary, the way black holes announce themselves is often dramatic and visible. Gas swirling into one heats up and shines brightly in 10th rays, fast jets can shoot out from the surroundings like cosmic fire hoses, and two black holes crashing together send ripples through space itself that we can measure. Astronomers also see stars orbiting invisible, very massive points and infer a black hole from that motion, similar to noticing a whirlpool by watching leaves dance around it. Black holes come in a range of sizes and play active roles in their neighborhoods. They can grow by gobbling gas or by merging with other compact objects, and the biggest ones sit at the centers of galaxies and help shape how galaxies behave. Still, they are not hungry monsters roaming space grabbing everything in sight. You would have to get very close for their pull to overwhelm normal forces, so they aren't a danger to distant planets. There is also an intriguing quantum idea that black holes slowly leak energy over incredibly long times, but for real astrophysical black holes that leakage is essentially negligible on human timescales. In short, they are extreme endpoints of stellar life, dramatic, complex, and a little bit like that stubborn stain in the sink you can stare at and study for ages, but which won't drip into your kitchen unless you move very close. White dwarfs and the slow fade of low-mass stars. Low-mass stars burn their fuel slowly and, when the fuel in the core runs out, the outer layers drift away and the leftover core becomes an extremely dense, hot object about the size of Earth but containing a mass comparable to the Sun. This leftover core is called a white dwarf, and it no longer burns hydrogen or helium in its center. Instead, it shines because it is still very hot, like the glowing ember of a once roaring fire that has been left to cool on a cold night. Pressure inside a white dwarf does not come from heat-driven fusion but from a quantum effect. Electrons are packed so tightly they resist being squeezed closer together. To keep things simple, picture a theater packed full of people who cannot all sit one on top of another. Their bodies create a firm pushback. That pushback acts like a structural support, preventing the star from collapsing further. Without that support the object would fall in on itself, but because electrons are stubborn in a quantum mechanical way, the star stays stable, compact, heavy, and quiet. White dwarfs begin very hot and slowly cool over long stretches of time, gradually shifting from bright white to red and then toward undetectable darkness. The cooling is a patient process. There's no dramatic fireworks for most of these stars, only a gradual fading, much like a barbecued coal that keeps glowing faintly long after the grill is done. Examples in the sky show this progression. Some white dwarfs still have a strong blue-white glow while others are much dimmer, indicating advanced cooling. In many cases the original star shed its outer layers in a colorful shell of gas, often called a planetary nebula, so observers see a bright core sitting inside a faint, expanding fog. Not every low-mass star follows a simple, quiet script. If a white dwarf lives in a close pair with another star, it can pull material from its companion and brighten suddenly in events called novae, and if it gains too much mass it may be pushed past a stability limit and explode in a type Ia supernova. Nevertheless, for solitary low-mass stars the common ending is a long, slow fade, a compact remnant losing heat, becoming less luminous, and eventually cooling toward invisibility. Think of it as the cosmic equivalent of an old lamp that still gives off a little glow, year after year, very slowly dimming until it no longer lights the room. Practical analogies help. A white dwarf is like a metal ball heated until it glows and then left to cool, while the process of shedding outer layers is like a tree dropping leaves that float away and catch the wind. A touch of humor helps too. These stars are the universe's elderly relatives who refuse to dance at parties but continue to hum quietly for a very, very long time. The end result is simple and elegant. After a long life of burning fuel, low-mass stars don't explode in most cases, they contract into compact, glowing embers and then fade, radiating away their heat until they become faint remnants of their former luminous selves. Heavy elements and stellar alchemy. Most elements heavier than helium are made inside stars, and those elements are the raw material for planets, people, and peanut butter. Simple atoms like carbon, oxygen, and iron are stitched together in stellar furnaces by a process that takes light atoms and fuses them into heavier ones. Think of it as a high-pressure kitchen where hydrogen and helium are the flour and sugar, and the star bakes ever bigger cakes. Everyday things come from this cosmic cooking. The calcium in your bones and the iron in your blood were formed in previous generations of stars, while the carbon that makes up your cells was forged in their interiors. It's true, your grocery list has a starring role in the universe. When a star fuses lighter elements into heavier ones, it releases energy, which is why stars shine. In the cores of medium and massive stars, layers form like an onion, each one burning a different fuel and making new elements. Layers near the center can create elements up to iron by repeatedly smushing lighter nuclei together. This process is efficient up to iron because each step gives off energy, like breaking even while building a tower of blocks. But iron is a stopping point. Building heavier elements from iron does not give back energy, so the simple fusion engine of a normal star can't produce the really heavy stuff on its own. The truly heavy elements, gold, uranium, and many others, require more extreme methods. Explosive events fling neutrons at nuclei so fast that atoms grab many neutrons in a blink, then settle into new heavy elements. These rapid captures happen in violent stellar explosions and in collisions of compact stars, where conditions are so extreme that the periodic table grows quickly. There is also a slower route inside aging, puffed-up stars. Over long stretches they add single neutrons to atoms one at a time, building elements like barium and lead step by careful step. Slow and fast, two different recipes, same cosmic pantry. Once made, heavy elements don't stay locked up. Explosions and stellar winds scatter them into space where they cool into dust grains and mix with gas. That recycled material later collects into new stars, planets, and even life forms. Meteorites sometimes contain tiny stardust grains that predate the solar system and carry the fingerprints of the stars that made them. Those grains are literal souvenirs from distant stellar kitchens. Your smartphone, your table salt, and the gold in a wedding band all have ancestors in those blasted and bloated stars. A bit romantic, and a little messy. Astronomers read these elemental stories from light and from rock. Light from stars shows dark and bright lines, unique signatures for each element, so scientists can tell what a star is making without visiting it. Laboratory analyses of meteorites give direct samples of materials formed in other stars. Together with computer models that simulate stellar conditions, these observations explain how different stars contribute to the cosmic mix. Small, mellow stars add certain ingredients slowly, while big, short-lived stars and catastrophic collisions provide the heavy spices. The upshot is clear and practical. The periodic table around you is a map of ancient stellar chemistry, and your daily life is sprinkled with tiny pieces of starlight, literally. Remnants and recycling, how stars seed new stars. When a massive star runs out of fuel and blows apart, or when a sun-like star puffs off its outer layers gently, the result is the same kind of thing for the neighborhood. Gas and dust are spread back into space. These leftovers come in different flavors: a violent blast from a big star, a glowing shell from a smaller star, and steady winds that carry tiny grains away, but all of them leave behind raw material. The gas is mostly hydrogen and helium, with bits of heavier material mixed in. The dust grains are the tiny solid pieces that will later act like seeds. You can think of these stellar leftovers as ingredients tossed back into the pantry of a galaxy. Shockwaves and stirring motions from those stellar events can squeeze nearby clouds of cold gas, nudging them over the edge so gravity takes over and a new star begins to form. A loud explosion is not always needed. Gentle pressure from a wind or radiation can also push and carve, shaping dense knots where collapse begins. In places like the bright clouds visible in telescopes, astronomers see newborn stars forming in clumps of gas that used to be part of older stars' outflows. It's a bit like hitting an overfull compost pile and finding that the motion makes a fresh sprout pop up. A disturbance can trigger new life. The heavier elements, carbon, oxygen, iron and many others, are forged inside stars and then return to space when those stars die, and those elements are, quite literally, the building blocks for planets, rocks, and living tissues. Dust grains act like tiny scaffold pieces, helping gas cool and stick together so larger clumps can form. Without that solid material, planet formation would be much harder. Your body, a planet, or a rocky cliff all owe their makeup to many generations of stars that mixed and remixed material. Think of it as baking. Earlier cooks produced flour and sugar, and later cooks used those same ingredients to make something new and more complex. Not every remnant turns directly into a new star. Some material drifts and spreads, slowly changing the chemical makeup of the galaxy over time. Still, the cycle is continuous. Explosions and winds add fresh stuff, clouds gather and collapse, and new stars then repeat the process. The galaxy acts like a very slow, very grand recycling center where old stars help make the next generation possible. It's comforting, in a cosmic sort of way, that the atoms in a child's hand or a backyard plant once rode on the winds from a long-dead star. The universe keeps passing the recipe along, with occasional dramatic flourishes and, yes, a little bit of cosmic composting humor. Stars across time, populations and galactic ecology. Many stars form from gas that has already been stirred by the deaths of earlier stars, so a newborn star often carries the chemical fingerprint of its ancestors. Some stellar generations started with almost only hydrogen and helium, while later ones contain heavier elements, what astronomers casually call metals, like carbon, oxygen, and iron that were cooked up inside older stars. Think of it like baking. The first batch was plain dough, and every later batch gets a little more chocolate chip mixed in as the kitchen gets restocked with leftovers from previous recipes. Massive stars act like the noisy neighbors of a galaxy. They live fast, shed material in strong winds, and finally explode in supernova blasts that fling new elements far and wide. Smaller stars are quieter and keep much of their mass locked away for longer, releasing it more gently at the end of their lives. The result is a continuous recycling loop. Gases are enriched, then cool and clump into new stars and planets. A garden compost pile is a decent analogy. Dead leaves and kitchen scraps turn into rich soil that feeds the next season's tomatoes. The location within a galaxy changes the recipe too. Disk regions, with plenty of cold gas, tend to host younger, metal-richer stars and ongoing star formation, while the halo and central bulge are often populated by older, more metal-poor stars that formed when the galaxy had less heavy material available. Stellar feedback, radiation, winds, and explosions can clear gas out of a region or compress nearby clouds and spark fresh star formation. It's similar to how a forest fire can both destroy trees and create openings where new saplings thrive. Nature is messy but effective. Star groups also tell the story. Open clusters are loose gatherings where many stars form together and then drift apart over time. Globular clusters are compact, long-lived groups that preserve an older generation's makeup. You could say open clusters are like a college class scattering after graduation, while globular clusters are like a tight-knit alumni club that still meets for reunions. Satellite galaxies and inflowing gas can inject fresh material, altering the local mix and sometimes triggering bursts of new star birth. All of this shapes a galaxy's long-term character. The balance between gas supply, star formation, and feedback determines whether a galaxy stays lively and blue with young stars or becomes dominated by older, redder stars. The heavy elements produced and dispersed by stars are the building blocks for planets and for chemistry that can lead to life, so cosmic recycling has direct consequences for worlds like our own. In short, the life and death of stars are not isolated events but parts of an ongoing ecological cycle on a galactic scale, Mother Nature, but on a cosmic budget and with slightly more supernova drama. Watching the sky, telescopes, spectra, and citizen science. Light is the main messenger astronomers use to learn about stars, and telescopes are simply tools that help us collect more of that light. Small, handheld binoculars will already resolve a lot more than your naked eyes, but a telescope with a good mirror or lens brings faint objects into view like turning up the brightness on a TV. Reflector telescopes use mirrors, refractors use lenses, radio telescopes use large dishes to catch invisible radio waves instead of visible light. A smartphone app can point out constellations while a backyard telescope can reveal craters on the moon and fuzzy star clusters that look like spilled sugar. It's practical, and a little addictive. Bigger telescopes gather more light and show finer detail, which is why professional observatories use very large mirrors or arrays of dishes working together. Think of a telescope like a bucket collecting rain. A bigger bucket catches more drops and shows you the pattern of the storm better. Magnification matters less than how much light you collect, so a small but stable setup often beats shaky high power. Cloudy nights, streetlights, and a wobbly mount are the real enemies. Stable tripod, dark spot, and patience win more often than a $100 eyepiece. You can even use a regular camera with a long exposure to bring out colors and structures invisible to the eye. Splitting light into a spectrum is like separating the colors of a rainbow to read a star's barcode. Those dark and bright lines are fingerprints that tell you what the star is made of, whether it's hot or cool, and if it's moving toward or away from us. When a star's light is slightly shifted toward the red or blue end, that shift signals motion, toward or away, because of how waves stretch or squeeze. Hobbyists can attach a simple diffraction grating or small spectrograph to a telescope and record these patterns. Consumer cameras and even some smartphone setups can produce useful spectra for bright stars. Think of it like comparing grocery barcode scanners. The pattern tells you the product, and small changes tell you if the barcode was printed crooked. Citizen science turns curiosity into real contributions. Volunteers help sort millions of galaxy images, flag supernova candidates, or monitor brightness changes in variable stars using online platforms. Projects hosted on public portals let anyone look at images, mark features, and submit classifications. It's the astronomical equivalent of crowdsourced proofreading. Amateur observers regularly report new comets, provide follow-up observations of transient events, and supply long-term monitoring that professional telescopes can't afford to do every night. Joining a local astronomy club or an online group provides mentorship, shared equipment, and experience with logging observations properly so professionals can use your data. Practical steps make participation simple and fun. Start with binoculars and a StarChart app, then move to a small telescope or a DSLR on a tripod for astrophotography. Learn to keep an observation log and how to submit data to organizations that collect amateur contributions. Light pollution maps and simple filters can improve what you see from a suburban backyard. Traveling to a darker site helps even more. And don't hesitate to ask questions. Experienced observers love showing others how a clear sky and a checklist beat a one-night wonder. In short, with modest gear, a bit of practice, and a willingness to share what you see, anyone can watch the sky, read the light, and help science. No helmet or astronaut training required. Quick recap: stars are born when huge, cold clouds of gas and dust slowly squeeze together under their own gravity. Think of a ball of dough getting kneaded until it warms up and starts to glow. Once the center gets hot enough, the star turns on and shines. Small and medium stars burn steadily for a long time, like a candle or a campfire. When their fuel runs out, they blow off their outer layers and leave behind a dense ember. Big stars burn fast and bright, then end with a spectacular explosion that scatters heavy elements like iron and gold, the same stuff in your blood and in jewelry, into space. Sometimes that explosion leaves an incredibly dense core or even a black hole that keeps pulling on everything nearby. If thinking about stars makes you look up and smile, you're not alone. These cosmic stories are literally part of us. If you enjoyed this, like and subscribe for more simple space stories, and tell me in the comments which part surprised you most or what you want to explore next. In the next video we'll take a closer look at black holes and how exploded stars seed new worlds. Yes, there will be dramatic fireworks and science. See you under the stars.